Hey there, how's it going? Terry Brown, Mechanical Engineering here with another engineering mechanics problem video solution. So let's have a look at the problem. All right, here's the problem. A little bit different to what we've seen before. A little bit tricky, but yeah, let's have a look at it and see how we go about solving this problem. So what we're wanting to do is to analyze the beam or the component AB, and we want to know what the reaction forces are at the connections at A and B. So at B, I think you should be able to look there and say, yeah, I know what I'm going to do there. A, that's a bit tricky. So let's see what we do. All right. So as always, the first thing we do is to draw the free body diagram because we need that in order to make use of our equations of equilibrium, because that's where our unknowns are drawn. We put on the directions of our forces and moments, and we use that to apply the equations of equilibrium. Right? So we want to solve for our unknown reactions at the supports. How do we do that? Right? We use the equations of equilibrium, hopefully you know by now. But yeah, to add equations to those general formulae, we need to have our free body diagram. So let's start by having a look at that. So when we draw a free body diagram, the free in that description means that it's free of everything that's attached to. So when we draw the free body diagram, the object that we draw a diagram of is just the component that we're wanting to analyze. So in this case, just this component A to B, right? Free of the roller support and free of this vertical post here where we have this smooth collar attached. Right? So I've seen students in the past in class exercises when they've gone to draw a free body diagram of this problem include all of this stuff here. Right? We don't want that. All we want is the component AB. Usually when you're drawing a free body diagram, after you've isolated the object that you're wanting to analyze, put on the dimensions for reference, some labels for the points of importance on the body, and then put on the known applied loads. Then you can start thinking about what's going on at the support. So I think with this one, we'll start with the support at B. So that should be fairly easy for you by now if you've done some work on rigid body equilibrium problems before. We know this is a roller support. The component can move horizontally freely, so no support reaction force in the horizontal direction, but it does constrain the component AB from moving in a rigid body way up and down vertically. Okay, so it prevents translation in the vertical direction. And in a second, we'll go and have a look at just the general description of how we analyze support for whether there's a force or a moment. Right, so you can see in our free body diagram, we've got vertical reaction force, give it a name, R subscript V, that represents the force applied by this support. All right, now let's go over here and have a look at this other end. So this is the end A here that's going to cause people problems. Let's go to the textbook and see what the general description says there about how we work out whether there's a force and or a moment. Okay, so here's the chapter of your textbook. So I'm using Hibbler's Engineering Mechanics Statics, and I've got the ebook version. If you're in my class at UTS, then in your Canvas page, there'll be a link to the relevant section in the textbook. All right, so let's go back to the textbook here. In a previous video, I went through all of these simple ones, the roller support and the pin support. This is something a bit different, right? So what we can do is to look at the table that you'll find in the textbook and see the different types of connections and see if you can match up the one in the problem with the one in the table in the textbook. So far, we don't have, none of these look like what we want. If you scroll down a bit further, here's one that looks like what we might want. Right. So here we've got a smooth rod and a collar connected to it. Here it's a little bit different because we've got a pin connection between this member here and the collar. Right, so this one might not be what we want. Let's continue down and see what else we've got. Pin connection. Here we go. So we've got a rigid connection between this part of the component and the collar here, and then our smooth rod. Right, so our free body diagram is going to be a force perpendicular to the rod and a moment reaction. All right, so you can just look at the table and then try and put that on the problem that you're working on. Or if we go to the definition, so if we go back up to here, there's these two statements here. So these two statements tell us how to work out whether we put a force or a moment or any type of constraint. What we look at here is if the support prevents translation, then there's an exerting force on the body. Right? So if we prevent translation, then there must be a force. If the support prevents rotation, then there must be a moment reaction. Conversely, if at a support something is free to move in a particular direction, so same as we had with the roller here, right? It's free to move in the horizontal direction, like this. So there's no horizontal reaction. Right? With a pin connection down here, it's free to rotate about the pin, so there's no moment applied. In your textbook, the other thing that you'll find, I usually have a really neat summary of the important points for each chapter. Here again, we've got those two statements about whether a support prevents translation or rotation and whether a force is developed. A reminder about how to draw your free body diagram, the fact that it's free from its constraints and other connections, and so on. Before we go back to our problem and see if we can apply this, while we're here, in fact, let's have a look at this, right? So thinking about those statements about how we work out whether there's a force or a moment applied or not. So this is a collar on a smooth rod. Right? This is free to move up and down along that collar. So smooth indicates that there's no friction or negligible friction. So no friction force here. So if it's free to move up and down along here, then along this direction here, right, there's no force, no reaction force to put. All right, so now if we think about, well, is this object prevented from moving in that direction? Yes, it is, right? So therefore, we must have a force. Right? So that tells us we need force normal to this smooth rod. Now, the other thing is, right, is this free to rotate like this? Okay, so in 2D, this is a bit tricky. So let me grab my little thing here, the best thing, or the closest thing that I've got to what I've got on the screen. So here we've got an object. Okay, let me turn it around so it looks the same as what's on the textbook. Right, so here's my object. It's free to move up and down. Free to move. So I've just got some holes in the paddle pop stick and this stick in my right hand. This goes through those two holes. Right, so it's free to move up and down. So no reaction force, tangent or parallel to the smooth rod. I can't pull it perpendicular to the smooth rod. So we've got a reaction force there. Now I can rotate it a little bit, right, in this model because I've got a bit of clearance between the hole and the stick. Right? And in practical application of this, right, you need to consider that. Right? Right? So here, for now, we'll just neglect that. But if I let go, right, you can see it doesn't keep rotating. Right? So there's a moment being generated by that connection to prevent the paddle pop sticks here from rotating. Okay, so that blue arrow that I've drawn on the screen is not what just happened then, right? It's not this rotation that we're talking about. Okay, around that smooth collar, right? So we're not talking about rotation about this way. That would be free, right? So there would be no torque reaction, if you like, right? But it is prevented from rotating somewhat, right, this way. Yeah? So we must have that moment as a reaction moment. Let's go back to our problem now. All right, so now looking at this here, we can see that the component AB is prevented from moving horizontally. So therefore we must have a horizontal reaction force there. We can just put it in the positive direction, or we can think about what else is acting on the beam and put it in the correct sense. Doesn't matter if you get it wrong. Your algebra will tell you if you get a negative answer that you just put the arrowhead in the wrong direction or the wrong sense. So we can see in this case that the only other force that's in the horizontal direction will be the horizontal component of our 200 Newton force here. So we can see that this force here will be acting to the right. We give that a name, so we can put that in our equation of equilibrium. So that's, we'll call that RA. No vertical force, right, because it's free to move up and down. Right? So no vertical reaction. It is, though, prevented from rotating, right, because there is some length to this collar, so that prevents that from rotating down. Like, so my hand here is at end A, sitting in that collar prevents it from rotating down. All right, so we need to put in there a moment reaction. You can put in the direction that you think it's going to go, or you can put it in as the positive direction. So normally we take anti-clockwise as positive, or you might look at this force here and think, okay, this force is acting downwards, so I think it might be going to go anti-clockwise. Doesn't matter if you get it wrong at this point. Your algebra, your equations and algebra will tell you whether it is actually anti-clockwise or clockwise. All right, so that's now our complete free body diagram. So now we can go and start to apply our equations of equilibrium. So let's, in this case, start with some of the forces in the x direction. So we need to indicate which sense is positive. So to the right for x is positive, and upwards for y is positive. So if we look at our free body diagram, we've got RA going to the right, so that's positive, minus the horizontal component of the 200 Newton force. Okay, so the horizontal component here will be adjacent to the 60 degrees, so therefore cos 60. Do our sums, and we get RA equals 100 newtons. Some of the forces in the y direction equals 0, upwards is positive. We have RB, and we have vertical component of the 200 Newton force. That will be opposite. If you think of our little right angle triangle here, that'll be the opposite side to the 60. So that's sine 60, remembering that it actually acts down through here. We'll need to remember that for when we go to calculate moments. All right, so that's all we've got for now. All right, now, note that if we had have gotten our free body diagram wrong and put a vertical force here, then our equations over here are going to be wrong. Right? So this shows you that the key step in the whole process for analysing things like this is drawing your free body diagram and getting that correct. So if you had have got this wrong over here, then this is going to be wrong. So rearrange, solve for RB, and get the value for that, 173.2 newtons. Next, apply our moment equation, and we're going to use our equation sum of the moments equals 0, we need to indicate which way is positive. So if x and y are defined to the right and upwards like this, then anti-clockwise is correctly positive. And we need to also indicate the point about which we're calculating moments. So let's do this now. So some of the moments about point A, we have the moment reaction, MA. Let's put that in, anti-clockwise. And then we have our 200 Newton force here. Now we could find the perpendicular distance. So if we continue the line of action down here and find the perpendicular distance down this way to that line of action, we could do that. But generally, the easier way to do it is to define the components of the force and then use usually the distances that are given. All right, so vertical component, 200 sine 60, acts at a distance of perpendicular distance to point A of 2 meters. That is it going clockwise or anti-clockwise? Again, if you're not sure, just get out a pen or something, hold it where you're taking moments about and push, see which way it goes. All right, so that's going clockwise. In that case, that's negative, and the horizontal component of this force, 200 Newton force, continue its line of action, passes through point A, so therefore it doesn't have a moment. So the next thing we need to deal with is the force RB out here. RB times 4. RB, perpendicular distance to point A is 4. Is it clockwise or anti-clockwise? Again, if you're not sure, just grab a pen or a ruler or whatever. Push where it's applied this way, so that's anti-clockwise. So that one's a positive moment, and that's it. So we can make that equal to 0 and solve for our unknown. So again, note, right, if we had have got our free body diagram wrong, got this equation for some of the forces in the vertical direction wrong, RB would have been wrong. We substitute RB in here, so then our moment would be wrong. Right? So vital to get your free body diagram right. Okay? And that's why we emphasize drawing free body diagrams so much when we teach engineering mechanics. All right, so substitute for RB, solve for MA, and we get minus 346.4 Newton meters. So this negative value that we get here indicates that we made the incorrect assumption about whether MA was clockwise or anti-clockwise. Now, if you go and think about it, if we had taken moments about point B, we can see that this 200 Newton force here tends to rotate about point B anti-clockwise. So therefore, MA needs to be clockwise if we're going to have some of the moments equal 0. Right? Noting that RA causes no moment about point B, right? Because its line of action will pass through point B. Okay, so going through that again, imagine taking moments about point B here, and you probably should do this as a check. I haven't done a check in this video solution, but if you redo the problem, take moments about B and solve for MA. All right, so anyway, so take moments about B. The 200 Newton force tends to rotate this thing anti-clockwise about point B, so therefore MA needs to be clockwise, right? Which is why we've got the negative value there. All right, so finish up by summarising your results, put your final answers, and round to 3 significant. All right, so that's it for this problem. Okay, so I hope that was helpful. A little bit of a more tricky problem than usual. Not your standard roller support, pin support, or built-in support this time. Had to be a little bit more careful about how we thought about supports, okay, with that collar on the smooth rod. And as I've stopped here, I've just realised I was going to show you something else. So the other thing that you should do, so in your textbook you'll see at the bottom here some examples of different types of connections. So in your everyday life, as in your work, as you're going about, just take note of the structures and machines and mechanisms that you see about you, and see if you can turn these real connections into the idealized connections and model supports that we have in the table. Right? So here you can see we've got a cable to a pin support. Here we've got a rocker instead of a roller, so free to move in the horizontal direction, but not in the vertical direction. So this would be modeled something like a roller. Here, this would be a pin support. So just keep your eye out for the different structures and machines and mechanisms and try to identify these. All right, that's it now. Again, if you like the way I go through these problems in some detail, then please give the video a like. Even click on subscribe if you want. Not for my benefit. I don't get any money from this. All the money goes to YouTube. I don't have enough subscribers per year to make any money. YouTube takes it all. But the thing that happens, as I'm sure you know, is that the YouTube algorithm looks at likes and subscriptions and then uses that to suggest the videos to other people. And I'll see you in the next video.